Hi everyone. Today we'll talk about limits at infinity. Let's start with two basic ones. The limit as x goes to infinity of 1 over x, and the limit as x goes to negative infinity of 1 over x. To compute these two limits, we'll use tables and graphs. In the first table, the inputs tend toward infinity. What happens to the outputs? When you plug in 1, you get 1. When you plug in 10, you get 0.1. Then you get 0.01, 0.001, and 0.0001. The outputs tend toward 0. You could make the same conclusion by looking at the graph of the function, or rather at the piece of this graph for x is bigger than 0. Note that as inputs tend toward infinity, the outputs get closer and closer to 0. So this limit is 0. In the second table, the inputs tend toward negative infinity. The outputs are negative 1, negative 0.1, negative 0.01, negative 0.001, negative 0.0001. The outputs tend toward 0. You can make the same conclusion by looking at the piece of the graph for x is less than 0. As the inputs tend toward negative infinity, the outputs get closer and closer to 0. So this limit is also 0. These two limits are two examples of limits at infinity. Before I show you how we can compute limits at infinity of more complicated functions, I wanted to mention that if instead of 1 over x, you had 1 over x squared, the limit would also be 0. If you had 1 over x to the third power, the limit would also be 0. And that is because as the denominator gets larger and larger, the whole fraction gets smaller and smaller, getting closer to 0. There are three major ways in which you can compute limits at infinity. Let's take a look at the first example. We need to find the limit as the inputs grow without bound of this fraction. As x's get bigger, the numerator gets bigger. It tends toward infinity. The denominator also tends toward infinity. So this limit is of the form infinity divided by infinity. The term in the denominator that matters the most is x to the third power. Imagine you plug in 10 to this expression. 10 to the third power is definitely much bigger than 10 squared, and it's definitely much bigger than negative 3. Mathematicians realized that if they factor the highest power of x in the denominator, both from the denominator and from the numerator, they can compute this limit algebraically. So what I will do, I will factor x to the third power both from the denominator and from the numerator. This is what I will get. The limit as x goes to infinity of, if I factor x to the third power from the numerator, I will have 1 over x squared plus 1 over x to the third power in parentheses. If I factor x to the third power from the denominator, I will get 1 plus 1 over x minus 3 over x to the third power. To confirm it, you can multiply these out. When you multiply these two out, you will get x plus 1. If you multiply the denominator, you will get the original denominator. The reason why this works is because now I can divide out x to the third power. And I believe the remaining terms, I know what happens to them as x goes to infinity. We discussed that 1 over x squared goes toward 0 because the denominator gets bigger, so the whole fraction gets closer and closer to 0. The same thing with 1 over x to the third power. The same thing with 1 over x in the denominator, and the same thing with 3 divided by x to the third power. All these terms go toward 0, which means that the numerator now gets closer and closer to 0. The denominator now gets closer and closer to 1 plus 0 minus 0, which is 1. So this is of the form 0 divided by 1, which is 0. This is the most rigorous and the most difficult way of computing limits at infinity. Let me show you a second way, which might be slightly easier, but follows the same idea. Now I'm computing the limit as x goes to negative infinity of this expression. Instead of factoring the highest power of x in the denominator from the denominator and from the numerator, instead I will divide each term by the highest power of x in the denominator. In the denominator, the highest power of x is 2, so x squared. What I will do now is I will divide each term by x squared. And I will get the limit as x goes to negative infinity of 1 minus 1 over x squared divided by 3 plus 1 over x squared. While this method is equivalent to the first method I showed you, this is usually much easier to do for the students. Now, as x goes to negative infinity, what happens to the expressions we are left with, the terms we are left with? We know that 1 over x squared goes to 0. So this appears to be of the form 1 divided by 3. So this limit is 1/3. Sometimes these two methods can be used to compute limits that are of functions that are not even rational functions. Take a look at the next limit. I have the function e to the power x in it. Recall that the function e to the power x looks like the following. It grows rapidly for x is bigger than 0. In fact, as x's tend toward infinity, the values of the function tend toward infinity. So I know that this numerator gets bigger and bigger. The denominator also gets bigger and bigger. This is of the form infinity divided by infinity. However, the term in the denominator that matters the most is e to the power of x. So I will divide each term by e to the power of x. And I will get the limit as x goes to infinity of e to the power of x plus 1 over e to the power of x divided by 1 minus 5 divided e to the power of x. The first term I obtained because e to the power of x squared is the same thing as e to the power of x times e to the power of x. And when I divide that by e to the power of x, I am left with just e to the power of x. Now, I can do the same type of analysis. This term gets closer and closer to 0 because the denominator gets larger and larger. This term gets closer and closer to 0. This term, though, gets closer and closer to infinity, which tells me that the numerator gets closer and closer altogether to infinity. The denominator gets closer and closer to 1, so the whole expression is infinity. I told you that I was going to show you 3 methods of computing limits at infinity. So far I showed you 2. To understand the third way, we need to know what a leading term of a polynomial is. Given a polynomial, a leading term is the term with the highest power of x. In the first function, the leading term is 3x to the 4th because that is the term with the highest power of x. In the second polynomial, the leading term is negative 2x to the 5th power because that is the highest power of x. Now, when we compute limits at infinity, the next theorem says that instead of computing the limit of a polynomial divided by the polynomial, instead I can compute the limits of the leading terms. Let me show you how this theorem works in practice. Take a look at the 3 problems below. If you would like to try them yourself first, don't forget that you can download these notes using the link in the video description. According to the theorem above, I must look at the terms with the highest power of x. That will be 2x to the 3rd power and x to the 5th. The theorem above says that instead of looking at the limit of this polynomial divided by a polynomial, I can look at the limit as x goes to infinity of the leading terms only, which is 2x to the 3rd power divided by x to the 5th power. Now I can simplify this expression. X to the 3rd at the top cancels with x to the 5th at the bottom, and I get 2 over x squared. And I know that gets closer and closer to 0 because the denominator grows larger and larger. Note that this theorem makes sense. We did say that the term with the highest power of x matters the most. That is why looking only at leading terms seems to make sense. Only the terms with the highest power of x matter as x's get bigger and bigger. In the second example, the leading terms are x to the third power and x squared. So this limit can be computed as the limit as x goes to negative infinity of x to the third power divided by x. Divided by x squared. Simplifying this gives me the limit as x goes to negative infinity of x. This is negative infinity. In the third example, the leading terms are, in the numerator, 3x to the fourth, in the denominator, negative 5x to the fourth. So this equals the limit as x goes to infinity of 3x to the fourth divided by negative 5x to the fourth. I can simplify this and I get the limit as x goes to infinity of 3 over negative 5. A limit of a constant is always that constant, so I get negative 3 over 5. I want to mention that this theorem about leading terms can only be used if you are dealing with an expression of a polynomial divided by a polynomial and you're computing the limit at infinity. If you're computing a limit at x equal to a, where a is a number, you cannot use this theorem.